Thanks, Chairman, for the introduction. As you said, my name is Giovanni Berselli. Just a few words about myself, my background. I'm a mechanical engineer working in robotics. I had the chance to work before going to Genova at the German Aerospace Agency, the DLR, at Harvard, at the Massachusetts General Hospital, and lately at the Technical University of Munich. As the slides say, we build robot hands of several shape and size. And first of all, my thanks goes to the PhD students of the team that I am coordinating, which are actually the soul and the heart of this research. My university is located in the northern part of Italy, on the seaside. This is a picture of Genova. And the university is quite old. And the lab that I am leading is called the Mechanical Computer-Aided Design Engineering Lab, which I proudly wear also on my shirt. We have 7,500 students. And also Genova is home of the Italian Institute of Technology, where we've been, we have an advanced robotics department. We've been building humanoid robots since several years. Maybe some of you might have seen or might have known about the iCub, which was a very first baby humanoid robot, was not able to walk yet, was just able to do like baby human do. We also build big ones, big humanoid robots for construction. And this is our way to get technology transfer from academia to also to industry. My talk today is about manipulation systems, so robot hands, or maybe devices which are not shaped as the human hand, but are used to manipulate objects. Devices which may be also intelligent. They may have built-in artificial intelligence. We don't just build hands, but we also build the design tools that help engineers to conceive them. Okay, so here you can see, for instance, an anthropomorphic hand, which is manipulating an object which is not rigid, is a soft object, a strawberry. Actually, the world around you is full of objects which are deformable, which are soft. For instance, these cables here are deformable objects. And to manipulate them is difficult. To automate the manipulation of these objects may be challenging. So, when I say that we build design tools to help engineers to conceive robot hands, that's what I mean. On one side, we have the digital world, so a digital replica of the hand or the gripper that we want to build. And on the other side, we have the gripper itself. This was actually a movie of a three-finger underwater gripper that was grasping a cylindrical object. The keyword are simulation to real, so sim to real. We want to move from the digital world to the physical world easily, and also to go back, so to replicate in the digital world what is actually happening in the real world. What are, the particularity of these simulations? On the one on your left, the fingertips are soft, like the palm of your hand. It's not rigid, it's soft. In the other simulation, the spherical ball, the blue ball, also that object is not rigid, is compliant, is soft, which is, an issue to solve when it comes to engineering. Here are some examples. So a 4-finger gripper whose design is optimized in order to pick up several objects at the same time. So not just one, but several of them, several deformable objects. So has been conceived, designed, and produced for such task. Another example, and the problem is the same. So we want to pick several objects at the same time. So one, idea is that we don't have to replicate the shape of the human hand. We can have something different, maybe several fingers. We can have a cage that constrains the object themselves. Other examples that go back to what I just said, which is something which is very, very hard to automate, is the manipulation of cables. If you think about it, there are several applications in industry where you need to manipulate cable, which are, let's say, an object with one dimension, basically, which is highly deformable. So here we are using artificial vision, we're using sensing, tactile sensing, to operate what actually at the moment is done mostly by human. And in all these cases, the gripper, the hand itself, is designed differently. But let's go to something which looks like the human hand. Once again, simulation and a real hand. This is dated. This is back from my PhD student days. So it's the very first hand that we produced with additive manufacturing. The black part is soft, are just they simulate the touch of the human hand. The other part is plastic. So this was our very first attempt to get a hand out of a 3D printer. Maybe from far away you could see some cables that are tendons that would lead the motion to the muscle in your forearm. This was our very first attempt. Okay, so here we have, let's say, somehow a problem that the design of these devices is not easy. These devices are plenty of components, they break easily. We will see later that they are very cost ineffective. They cost a lot of money. And it's not that easy to move from the virtual world to the physical world. So it ends up, being a problem for us having to build, being the problem from the student that they have to pass the exam. So the problem is, can we make it simpler? So this is an example of the most, let's say, stupid gripper we conceived. So basically, it's one piece. It picks up, it's a pick and place task, picks up an object, and then leave it on another side of the table, for instance. What is the peculiarity of this gripper? The peculiarity of this gripper is that it is produced in one piece only. So it's very, very inexpensive, and if you have the file, the computer-aided design file, you bring it to the printer, to the 3D printer, and that's what you get. So this is the, let's say, the meaning of this picture, that maybe, our dream is to be able to print an artificial limb which is rapidly prototyped, maybe in one piece only. Why not disposable? If it's really cost effective, you can just throw it away whenever it breaks. In order to simulate these guys is not that easy. I will not go into details of modeling equations and stuff, but that's what we spend our time doing, to try to simulate the shape of these grippers and then bring them into the world. So basically, what we're trying to do is to move our design philosophy from a world which is rigid to a world which is soft, deformable. This is, once again, an instance of an anthropomorphic hand produced at the IIT, at the Italian Institute of Technology. For instance, if you go and try to shake hands of Sophia, the humanoid robot that we just saw on stage, the hand of Sophia is like this. So it's done with rigid objects. It's not deformable, it's not soft, it doesn't feel like your hand. Okay, so basically, we're moving from what I teach to my students at the first year, and then also the third and then the fifth year, that metal doesn't lie. So if you use a material which is rigid, you will end up with something which is, reliable, but unfortunately several components and very cost ineffective. Whereas we want to move to a world which is soft, which is compliant, flexible, which is adaptive. This is not taken from our lab. This is an example of an industrial gripper, which is produced by Festo, which adapts to the shape of the object to be manipulated. If you think about the problem of moving to traditional design to soft design, it ends up on which material you will use to produce your hand and which morphology you will use to produce your hand. So this is a didactic example. This is one piece, gets out of the printer like that. And it's very difficult to understand how it deforms. That would deform exactly like your elbow. Okay? So in order to conceive this shape, you have to be able, to do our job, basically. But in case you are able to do it, you will understand that it does deform like your elbow. And it is produced in one piece, and it is cost-effective. And it's all about morphology. It's not about material, it's about morphology. So, moving from rigid to soft, and these are two examples that are taken from the lab. So this was a 3-finger hand that we produced 20 years ago for the European Space Agency, which is 3-finger and rigid. And underneath, the soft hand produced by a colleague of mine, which is Professor Antonio Bicchi from the University of Pisa. And you can see the fingers, they can deform. These hands would feel like your hand, like human touch, in case you use it. And what we do provide tools, design tools, that can be used also by non-experts, that basically, in theory, they would touch a button and end up with the perfect shape of your hand. There is this, let's say, paper, a scientific paper, which dates back from the 90s, which is called Hands for Dexterous Manipulation and Robust Grasping, a difficult road toward simplicity. We need to do whatever we can to make these hands, this robotic device, simple. This is the key word. So in the next slide, I will show you my personal road towards simplicity, also by showing some shapes which may be difficult to understand for non-experts. That finger on your left dates to 2012. It was our very first attempt to produce one single finger from 3D printing and reliable. It was not reliable, it was breaking very, very easily. Our very first hand with soft palm and tactile sensing dates to 2014. We called it DexSmart hand. We were using for bimanual manipulation. That is the very first prototype of a single finger produced in one piece only that was not breaking. So if you have the file for that finger and you have a 3D printer at home, which now is like 300 euros, many makers, they have a 3D printer at home, you can just print your finger. This guy, whose shape is very, very, let's say, peculiar, is a wrist. It moves like the human wrist moves. This was the very first idea we had. If you once again go back and try to shake the hands of Sofia, you will see that she doesn't have a wrist. She just has the hand, but not the wrist. And here you can see the advancement that we did in having a mechanical device that would move and would feel like your wrist. And here, finally, one piece only. It took a lot of effort to get to that stage, but the guy on your left bottom, it's a one piece only robotic wrist. That is a monolithic finger produced in one piece only, extremely reliable, would not break. And then we moved on. We went to fingers whose stiffness can vary, the rigidity of the finger can vary. You can do it yourself with your hand. You can make your finger stiff or compliant at your will. That's what we did. And then we moved to something which is not even anthropomorphic. It looks like a gripper, indeed, not a hand, which is, let's say, our attempt to solve a very general problem, to be able to manipulate objects of very, very different shape and size. Also, that guy, even if it's not trivial, is conceived in order to minimize the number of components. And we also went back also to try very, very difficult shapes that are, once again, optimized in order to obtain what you want. Also, this guy, which is very difficult maybe to understand, is a wrist. Is a wrist where you can switch on and off the motion. So you will be able to move the wrist on back and forward, or if you want, in 2 degrees of freedom, as we say in engineering. So once again, paradigm shift from robots which are rigid and fabricated to robots which are formed. So 2 examples. This is, let's say, the conceptual design of a robot hand, which is compliant, is soft. The keyword DOA signifies degrees of actuation. It means how many muscles, how many motors do you need to power the device. So you will have one motor for the elbow, 2 motors for the wrist, and 4 motors for the hand. And what is the thing that we are trying to achieve? The thing we are trying to achieve is cost reduction. If you think about it, robot hands, like that, they are shaped like human hands. They're used for possibly 2 applications: humanoid robots like Sophia, or prosthetics. If you use a robot hand for prosthetics, you have to be able to give the hand to the people that actually need it. And the people that actually need it might be people that are not, that they cannot spend that much money. At the state of the art, an anthropomorphic prosthetic hand, let's say an inexpensive one, is about 20,000 euros. Inexpensive one. That is obviously something that, if possible, you would like to decrease as much as possible. Okay, so the roads towards simplicity for my experience. This is the wrist, and that's, I'm sorry that you will not see the movie again, but this is all the procedure of which I'm not going to spend a word on, but is what we spend our time on, building equations in order to get the right morphology. It moves beautifully. It moves exactly like your wrist, and is one piece only. It gets out of the printer as is. The procedure is patented. We get out with a morphology. You go to the printer. You get the wrist. Elbow. This is our prototype of an elbow. Once again, it's not rigid. It's compliant. If you go and shake the hand of this robot, the elbow will move, will not stay there. So this is something that, once again, if you go and try to shake hands of humanoid robots, most of them, they will not behave like so. They will not follow your motion. Okay, bio-inspired wrist, then we wanted to take the thing even further, so to maximize the motion of the wrist even beyond the human capabilities, and that happens also for the finger itself. Okay, one other application before I leave the stage is compliant grippers. So now we are taking a step backward from something which is anthropomorphic, which resemble the human hand, and we try to produce a device which can be used for several applications. We call it the University of Genova gripper, and these are version 1, version 2, that was just produced in 2025. You've seen this video already, so basically the concept is we want to have a device that grabs everything, that grabs anything. Okay, so here you can see that it has 4 fingers, but they are reconfigurable. You can reconfigure them in the way that you want. Not just that, it can grasp and hold objects which are fragile and do not let them go. Here you can see an example of an orange and an element whose shape I'm not going to talk about, but has been optimized in order to be what we are looking for, and has applications, for instance, in agri-food or for the space. Okay, here you can see that it truly grabs several objects. Also fragile objects. I won't spend the word, but the gripper is, let's say, equipped with tactile sensing, so it can feel the force that exerts on the object itself. It can grab several objects at the same time. Here they are grabbing 3 balls at the same time. Obviously, we gave up anthropomorphism. We gave up anthropomorphism. We don't want the gripper to look like your hand, but to be as flexible as possible. Okay. So we're not selling the gripper, but just out of curiosity, we're not the only one that, have this expertise in grippers. So we took a look to the state of the art and the grippers that are produced by industries, not by academia, in terms of reconfigurability, multi-object grasp, shape conformability, and sensor feedback, tactile sensor. And we can say that we tried at least to build something which is better than the state of the art, also in terms of cost. Okay, that's a figure of merit, a KPI, which for us as, let's say, mechanical engineering sometimes doesn't count, but in this case it does. Those are grippers which are sold. For instance, the Shadow DEX-E is very, very new. It's a beautiful piece of engineering, but unfortunately very expensive. So, visual summary. Basically, we tried our best to provide novel solutions, possibly one-piece only solution, to build robotic devices for manipulation of objects. We call it mechanical intelligence instead of artificial intelligence, because we are building mechanical devices which are themselves intelligent, that they can adapt to the world. So they are built inside the material. Okay, once again, the wrist, another prototype of wrist done by my student, the elbow, which can vary the stiffness. So, takeaway message for this talk. Mechanical simplicity may mean geometric complexity. So these robots that we are building, outside they resemble the human hand, inside they are not so, the morphology is not so trivial. We develop pragmatic design methodologies to help also, as an academia, to help non-expert users to use these tools and to build their own hands. Now, for instance, we are developing the overall arm of another humanoid robot. Maybe you haven't heard about it. It's called Robi. It is produced by an Italian company. And here, once more, you can see a glove, soft glove, which can be mounted on the top of an existing hand in order to provide tactile sensing, tactile feedback. Okay, so I would like to thank again my PhD students. That means grazie, that means thank you in Italian. And this is a sculpture that stands on my desk, to remind our dream to produce a robotic limb in one piece only, maybe by 3D printer. Thank you.
Ladies and gentlemen, Giovanni Berselli. Giovanni, I have one question for you. So these developments are absolutely, groundbreaking, really impressive. But what challenge remains in building robotic arms/grippers?
One of the main challenges, I've been working on robot hands and grippers since 20 years. One of the main challenges, which is still technologically unsolved, is the sensing part. So I haven't seen yet any tactile sensor which is actually reliable, which would last. So if you go to the world of prosthetics, most of the users, they would just use either the hook or a cosmetic hand or a very, very simple robotic device. So it ends up that most of the technological solutions that we are developing, they don't truly go into the real world because they are either too expensive, unreliable, or they are too difficult to manage. Tactile sensing, there are several possibilities to produce tactile sensors, but none of them actually solves the problem. That's an open door in science and technology which needs new ideas, in my opinion.
Well, once again, thank you so much for a really inspirational presentation. Let's give him one more round of applause, ladies and gentlemen. Thank you so much.
Thank you.
Thank you.
Thank you.